All right, class, we are going to take a look at section 4.2 today. Before we do that, take a second to do this warm up. And by take a second, I mean maybe take a minute or two. There are a few things to do here. Go ahead and pause the video. And just note that if you want a hint here, that there are a number of things that have to be done if you're going to verify. I guess I've kind of said it in the warm up, but there are a couple things that need to be done if you're going to verify that all four of those things are solutions and that they form a fundamental set of solutions for this differential equation. You need to check each one of them and make sure that each one of them satisfies the differential equation, of course. And then you also need to check the Wronskian and make sure that they are linearly independent set of solutions. So we'll do this similar to how we did in class the other day. We'll check the first one, of course, is easy to check. Its derivatives are 0 all the way down. And if we do that, if we form this linear combination of those things right here, of course, we'll get 0. And now we do the same thing with t. Its derivatives are 1, 0, 0, 0 going down. And of course, that gives us 0 as well when we plug that in to our equation. Now let's try e to the negative t, finally one that's a little more interesting. Though the derivatives are not too tricky here, we just get this kind of alternation going. And so now we're going to do, I guess, okay, what's the recipe? We're taking one of these plus two of these plus one of these. Do you see how those will come out to be 0? And then the last one is takes a little bit of a product rule to resolve, but you can check my work on these. You get kind of each time that e to the negative t term kind of explodes and part of it combines with the front term. And so checking those derivatives gives 0 as well. Take a second to verify that that's true. This actually takes a moment to make sure it's right. But again, you're taking one of these plus two of these plus one of these, and I think you'll see that all of that cancels out nicely. Okay, now we're taking the derivatives, loading them in here as well, the functions, their first, their second, and their third derivatives, loading them into that Wronskian matrix. We're going to take the determinant, and again, like I've done recently with some other similar ones, I'm going to do this determinant by expanding down that first column. So then that ends up just being the determinant of this 3 by 3 matrix here in the corner. Right there. 1 times that. Of course, now that matrix also has a bunch of zeros in it, so I'm going to end up doing this 1 times the determinant of this square matrix. And so now it ends up just being really just this 2 by 2 determinant, which is, what does that all come out to be? Well, it looks like we get e to the negative 2t, and then we get that t e to the negative 2t part canceling out. So then the question is this non-zero? And the answer is yes. E to the negative 2t, no matter what t is non-zero. So we've done it. Now, before we get into our lesson, I'm going to ask us to do one more bonus warm-up. I know I haven't even gotten to the opening slide of our lesson yet, but I think this is really important too. Now, if you did the pre-calc lesson, then hopefully if you really looked at those slides and you really kind of refreshed your memory on all these topics, then you might not need to do this, but this is especially important for one thing especially that we're going to do today, which I kind of have a feeling that you might not remember real well. So this is going to highlight a really important idea. Here we go. So how would you expand this? This is maybe the first and most natural way you would expand this. You'd be like, okay, well that means you would multiply it by itself 3 times, and then maybe you start working on it, right? You multiply 2 of the binomials together. I just multiplied the second set of, the second and third set of brackets together, combining like terms there and resolving the I squared, all those things. So you can just verify that I've kind of cleaned that up nicely. And now I'm going to finally multiply the first set of brackets by what we got from the other part. So here I'm deciding to approach it by multiplying this by 1, and then this by negative 2I root 3, and then this times just the negative 3. So you can see that. And now I'm going to multiply each of those, to kind of distribute again. And now combining like terms gives us, well, look at some nice things that happen. This and this, here I'll actually highlight them. These go away. Yeah? And so we just get 8. Wait a second. 8. Okay, well, hopefully you figured this out yourself. You paused, you did this. It's pretty exciting, right? To just get 8 after all that. There are a couple interesting takeaways from that. When we get 8 at the end, we kind of think, first of all, that's really cool that such a thing would happen, that we'd just get like a really nice number 8 after such messiness happening. But whenever that kind of thing happens in math too, you kind of wonder, man, am I kind of like missing some kind of underlying thing that's happening? And the answer here is like definitely yes. There's like something going on here, but you have that suspicion that something could I have known that this was going to happen somehow before I even started? Like, what's going on here? Is there something kind of simple that I'm missing? Is there maybe there's even some geometry of this problem underlying this that's governing why this happened? If those those ideas are entering into your mind, you are completely right. Okay. The other takeaway from this is to think, okay, well, we've got something when you cube it that gives you 8. That is negative 1 plus I root 3. When you cube it, gives you 8. Now, there are other things that when you cube them, give you 8. Like, how about the number 2? Like when you cube 2, you get 8. And so for the number 8, we would say that 2 is a cube root of 8. Now, before today, or many people would say like, oh, the cube root of 8 is 2. But really, like there's a sense in which 8 has 3 cube roots. We just don't talk about the others very much. One of them is 2, but it should kind of be true that there are 2 other things that when you cube them give you 8. And that's absolutely the case. And one of them is this one right here, apparently. This number right here, negative 1 plus I root 3. So I think now we might think, well, maybe there's a third one, so we'll have to think about what that one is too. We won't address that right now. But yeah, apparently we now have we kind of have 2 cube roots of 8 that we've come across. 2 and also negative 1 plus I root 3. Let me show you a second way, which I think is going to be more important and illuminating for us. The second way is going to be to convert this to this complex number, negative 1 plus I root 3, to polar form. And the way I'm going to do that is I'm going to say that that number is, well, I want you to think about it. If you thought about the point x, y equals negative 1 comma root 3, right? Like as an actual point in the plane, in this case, like in the complex plane, like the point negative 1 comma root 3, where x is negative 1 and y is root 3, how would you convert that? How would you go about converting that? This point here, I'll do my best to write here, even though I'm using my mouse. Okay, how would you go about converting that to polar form is what I'm asking you to do. Now remember, by convert to polar form, I really almost mean like kind of take a component form, if you will, and convert it to magnitude and direction form. That's one way of saying it. So when we're doing that with a complex number, we can write it in this form, like find the radius, so to speak, like the distance this point is away from the origin in the complex plane. And you can do that just by using the Pythagorean theorem. And if you do that, you'll get 2 for this, like the distance this point is away. You can pretty quickly check that. And you can also think either by inspection or by using some trig that this is an angle then, I guess, that has a cosine of negative a half, right? Like, remember the definition of cosine, it's x divided by r. So in this case, that would be negative 1 divided by 2. And it has a sine of root 3 divided by 2. Okay, perfect. So with that in mind, those two things, what angle is that? Well, of course, that defines a very unique angle in the complex plane, or at least unique location. And that location, I think you would first say, oh, that's 2 pi over 3. Obviously, there are other angles that have that name, though, but we'll call it 2 pi over 3, or anything, 2 pi plus that. would work too. And now the application of what we're about to do here is very slick. We're going to raise this to the third power. Obviously 2 to the third, that makes sense. But inside here, we're using, this is the use right here of de Moivre's theorem. And I'm not going to go into proving it again right now. Hopefully you look through my my pre-calc PowerPoint and those, where we talk about how that's proved. It's actually a nice proof that involves some trig and anyway, so I won't go into it again right now. But it turns out, though, that de Moivre's theorem tells us here that when you raise a complex number in polar form to the third power, the R value gets taken to that power, but the angles get multiplied by that power. So that's why 2 pi over 3 is becoming 2 pi here. We're multiplying it by 3. Yeah, I mean, I guess in general, addition of 2 numbers in the complex plane, when you add 2 numbers in the complex plane, what happens is their angle values get added, right? Like there's one of them has an angle to it, and the other has an angle to it, and the sum of those two, or excuse me, the product of 2 complex numbers in the complex plane will have their angles will sum, and their R values will multiply when you multiply 2 complex numbers. I don't know. I didn't say that very clearly. It's all, like I said, I have it in a long form in that other PowerPoint. Well, clearly that comes out to be 8 as well, but I know my explanation took a minute to do. But in the end, actually, I think you'll agree that this is actually the better and quicker way to do this. I think you may already be convinced just by this problem that this is a great way to do it. Even though there's no mention of polar in this problem, it actually kind of makes sense to take our problem, convert it into polar, do our arithmetic, in this case, taking it to the third power, and then come back to like rectangular form. And like going into polar land is like worth it because it makes the computation so easy. And you can imagine this is really true if I were to take this to like imagine I had instead had asked you to take something like this to the 5th power. Okay, well then now it becomes really clear that what you want to do is put it in polar, take it to the 5th power, which is super easy, and then come back to rectangular. Imagine doing that with like expanding binomials, 5 of them, and resolving all these different non-real elements of it and having them all cancel out. And so hopefully I'm in the progress. If I haven't already done so, we're convincing you that this is the kind of the way to go, way to. So today we're going to talk about 4.2, homogeneous equations with constant coefficients, and all that like kind of pre-calc stuff that I keep hinting at is going to come right into play, including, like it says in the box, de Moivre's theorem, which we just referenced. So when we're solving a higher order equation, of course, it's going to have an associated characteristic equation. And it maybe goes without saying that the characteristic equation is going to have a degree that's equal to the order of the differential equation. So if you have in this case, for example, we have a 3rd order equation. So what characteristic equation are we going to get? Well, of course, we're going to get a degree 3 characteristic equation. So there it is, of course. There's the degree 3 characteristic equation. Remember, this is kind of emerges from us applying the same kind of principles as that we did with the 2nd order equation. We start by saying like, okay, well, let's let our solution be y equals e to the rt, like, and we kind of say let's try that, and then when we try that in there, you get kind of these r's popping out by the chain rule, and we get r when we take the derivative once, we get 1 r popping out, or twice or 3 times in the case of this term right here, we'll get that r cubed popping out, and that e to the rt will factor out. It can't be 0, and so all we're left with is that characteristic equation. So like I said, I won't go through that logic again, but it's the same logic that we used in our 2nd order equations. And now we're going to factor that, and we're just going to solve this. So this really is pretty straightforward generalization of what we did in our last unit. Do you see how to factor that? You could go into trying to do some more complicated things with trying to find a root and then, I don't know, using division or something. But here there is a nice technique. Do you see it yet? Maybe factoring by grouping is your hint. I don't want to, if you have a chance to do it, go ahead and do it here. Yeah, we can see that there's this factor of r minus 3 that can be pulled out. And then we have a full factorization there. And our final answer is, well, our roots are, of course, 3, 1, and -1. And so you can see that constructing the general solution here with 3 constants feels just really familiar to us if we've done the last chapter with second order equations. You just do C1 e to the one of the roots times x plus C2 times e to the another root times x, and so on. And the fact that there are 3 is no big deal. Now, we'll have to kind of highlight some of the other snags that can come up, right, with the complex roots, with repeated roots. That's kind of where we need to go as well. All right, so let's do this one here. We've got an opportunity to solve another one of these, very similar, and also notice that it's an initial value problem. So go ahead and you can think about it for a second here. The characteristic equation is, of course, that. But see, now here's where we need our kind of our pre-calc skills back on us here. This one doesn't kind of yield to a nice factoring by grouping trick, does it? So what are we going to do? Well, we have some other tools from pre-calculus that maybe we could employ. So one thing that comes to mind is you could try to find just even one root somehow. Like, can you find even one solution to this? If you can find even one, it's cubic, then that'll kind of unlock it, right? If anytime we have a cubic and we find one root, then we can do division, and then we have a quadratic, and no matter how terrible that quadratic is, we're going to be able to solve it. So either by inspection or using the rational root theorem, maybe you can notice that r equals 1 just like works, right? And the rational root theorem, again, a plug for the pre-calc PowerPoint that I put out there. The rational root theorem is something that you learned first back in Algebra 2, and then hopefully, I don't know, maybe it came up again in pre-calculus, I hope. So we'll maybe say some more about that in a minute. But one way or another, for this one, the good guesses someone might make, if there are any rational zeros at all. Now, there's no saying that a cubic could have irrational or non-real solutions, right? And the rational root theorem says nothing about this. But by the rational root theorem, at least, we have the possible roots. If there are rational roots, then they must be on this list, plus or minus 1, plus or minus 2, or plus or minus 6. So that provides, like, if they're going to be nice roots, they would have to be on that list. And that provides kind of a nice list that we can use as a starting point for making some good guesses. And of course, the first thing you might even try from that list is positive 1, and you would right away find that it works. Or, like we said, maybe just notice that it works. Look at that. Now, let's actually do division. Another opportunity for a pre-calc review. You can do long division here, or here I'm demonstrating synthetic division, since I think a lot of you find that to be quicker and preferable. So I would encourage you, though, to maybe challenge yourself and remember why it works. I always find that it's often true that many pre-calculus students who are doing this, or honors algebra 2 students, or whoever they are doing this and they're great at it. But if you were to press them on it, they would not be able to explain why. And so I challenge you on that. One way to figure out why it's working is to do the long division and to do the synthetic division next to each other. I have some other kind of hot tips for you too, if you ever want to talk about that with me. I'd love to chat about kind of why this works. But again, that's not the focus of this lesson. We're trying to teach differential equations here. Hopefully you know how to kind of attack factoring something like this, even if it involves the rational root theorem and division and things like that. So we drop that first 1. Now we're going to multiply 1 times 1, this times this. You're not going to really tell that I did that, but there it is. Okay. And now I add, and now I multiply again, this time 1 times -5. And now I add, and now I multiply again and add. So that gives us, of course, 0 at the end, because we kind of already knew that. We knew that if we plug in 1 that we get 0. And now we can see that that factors this way using the result of our division down here as well. Right there. And then that conveniently factors further. So there we go. There's our general solution. But wait, oh boy, Mr. Chase, really? We're not done? We have to, yeah, maybe we forgot that this is an initial value problem. So here we go. Let's solve the initial value problem. So we've got, as we expect, three initial conditions. So we're going to need to take the first and second derivative. And now we apply our initial conditions. If you plug in 0 for t everywhere in the first of these equations, you should get 0 for y on this side. So that's what I've done here. And now we're going to plug in 0 into this equation, the second equation, in for t. And we'll get also 0 for y prime. So that's the result of doing that right there. And then last, we're going to plug 0 in for t in this last equation, and we should get 2 for y double prime. So that gives us a system of three equations with three unknown variables. So how are you going to solve that? Do you have a favorite method? Honestly, it's a pretty nice system. And these always involve a bit of work, even when they're kind of really nice. So maybe just because of those C1 variables that are there, it seems like maybe some elimination would be pretty quick here. You're welcome to try whatever you like. You could do kind of multiple different substitutions to get it to, or I might also recommend row reduction. So that's actually what I did on a piece of paper off to the side. I'm not going to go through that. Again, this is the kind of thing that I expect that you, using some technique, are able to solve a 3 by 3. You could use inverse matrices too, and use your calculator. I don't know. There are lots of different ways to kind of go about this. Using the method of your choice, you should get that this is true. These are the constants. And so we're done. Just apply those constants to our general solution, which is over here. And we'll get that. Okay. So what happens when we have a repeated solution, a repeated root in our equation? Remember that in our last chapter, this is kind of what we wrote. Right? We said, okay, it's going to C1 e to the Rx plus C2 x e to the Rx, and we had to like multiply by x. Maybe that was like kind of a mystery at first, and then we did the reduction of order method, and you saw why we were able to get like where that kind of came from, why we need that extra x. Or also you could kind of think, we need them to be like linearly independent somehow, and that kind of does the trick by multiplying through by x, multiplying one of them by x. We need a second linearly independent solution, and that's kind of the trick that worked. Well, you can imagine, let's say you have a triple root, because now that's possible. Obviously, that wasn't possible at all in the last chapter when we were studying second order equations. But now, it's possible that we could get like a triple root in our situation. So if that were to happen, and so on, then we would multiply, of course, by like another x. So just making you aware that that's what we do. It's probably what you would have done, even if I didn't tell you. All right, so let's try another one. And do we see right away what the characteristic equation is? Yep, it's that. Why don't you take a second, pause the video, and see if you can't use your pre-calc chops to get that factored. Okay, well, yeah, it doesn't factor real nicely by grouping, really. That's tempting, but it doesn't really factor by grouping. Some of you might recognize it as a factoring pattern, though. You might actually recognize that it's something expanded. There's something special happening here. But if not, let's just try and do what we did before. Let's like make some suggestions of some good guesses. Like if we were using the rational root theorem, I might guess, well, 1 plus or minus 1, plus or minus 3, plus or minus 9, plus or minus 27 as like some good guesses. So I might try 1, for example. Drop the 1, multiply, negative 8. Okay, do you already see that this is kind of not going to work? This is not going to be equal to 0 at the end, so I don't like that. What about 3? We could try that. We could also try negative 1. I think you'll see the negative 1 doesn't work. So you try a couple things, right? You do this kind of thing with maybe an eraser nearby. So we check 3. This is Already you're kind of feeling that this is promising, aren't you? We get to drop the 1, multiply 3 times 1 is 3. Negative 9 plus 3 is negative 6. 3 times negative 6 is negative 18. Now we add, and now we multiply 3 times 9 is 27, and when you add those, you get 0. Hooray. So remember, when you're doing a cubic, if you find even one 0, then you've kind of unlocked it. So now we've got that. Oh, wait a second. This is r minus 3 times r minus 3 times r minus 3. Okay, so this is that situation we were just talking about where we have a repeated root, yeah? And so it's exactly, we queued this up, didn't we? This is exactly the situation that I just referenced on the last slide. What do you do if you have like a triple root? And the answer is, you can't just do like c1 e to the 3x plus c2 e to the 3x again. Those are the same things, right? We need a second linearly independent solution. And now we need a third linearly independent solution as well. So you just have to keep multiplying by more x's. Another example. All right, well, let's take a look at this one. Of course, the characteristic equation is going to be r to the fourth plus r squared equals 0. Factoring this is fairly straightforward. So we get some non-real roots here. And notice that we have like a repeated solution in there. We've got lots of good stuff going on here, right? We've got c1 e to the 0 for the 0, and then we got c2t e to the 0. And then we got a cosine and a sine there with e to the zeros that don't contribute anything. So notice the presence of a t, and I think this was, you guys, I think this was the example that we did. If it's not, it's really close to the example that we did in our 4.1 lesson, where I didn't ask you to solve it, but I asked you to verify that what the general solution was. And I remember the 4 solutions we had were 0, 1, t, cosine t, and sine t. And you checked all of them in our table, and all that. So we've just solved it here from scratch using the techniques of just like factoring, characteristic equation, all that. All right, the last situation, of course, is like what would happen if you had like repeated non-real solutions? Well, the answer is that wasn't possible in our quadratic when we had only characteristic equations that were quadratic. But now it's possible that you could have like a repeated non-real solution, I guess, too, right? So in those situations, let's say that a plus bi was a root, but also like a plus bi was a root again. Like it was a root twice of a polynomial, and also a minus bi. In that case, then of course we have what we normally have, but then we also have to get some more linearly independent solutions. So we're going to multiply by this x here again. And what happened if you imagine there was a non-real root that appeared 3 times? Well, boy, it would have to be of degree 6 at least, right? But so it might not happen at all, but it certainly would work. You could multiply by an x squared if you wanted. Not sure that'll come up. All right, let's write the general solution for this differential equation. Let's start by just looking at the characteristic equation and see if there's any kind of weigh in on it. I'm just going to tell you right now, it's not obvious how you would figure these out. So I'm just going to tell you right now that this has, because we're trying to illustrate the point here, this has two sets of conjugate pairs of non-real solutions, 1 plus 2i, and then also another 1 plus 2i. So with that in mind, this is an example of that last situation, right? Then our general solution would be this, right? Where notice that we would have like what we normally do from our last unit, but then if it's a repeated root, then we've got to introduce this like extra x term so that we get additional linearly independent solutions. That's about all we want to say about that. I mean, this could get really messy, and I'm not sure how practical it is. I'm trying. Will it come up much? Yeah, it's kind of a special thing that could happen, but okay, let's do another one. This looks not too bad. R, what is it? R cubed plus 8, I guess. Yeah. Well, this looks like this looks simpler than all the rest today. So we get R, I guess, yeah, how do we solve that? R cubed plus 8. So we get that. We get R equals -2 as a root. And then, well, what else? I guess we kind of want 3 roots for this. We kind of expect there to be 3 roots. So certainly one way to do this would be by dividing. We have one root, it's a cubic, so um, this cubic expression should be divisible by r minus 2. In fact, some of you just know, maybe it's not division, if you want to think about it just as like factoring. Some of you just remember how to factor r cubed plus 8. And it looks like that. You're like, Mr. Chase, I'm already done. I did it before you even said it. Yeah, good for you. Good job. All right. Well, one way or another, or if you didn't remember the factoring pattern for a sum or difference of cubes, that's fine. You could just do it by division. But one way or another, you've got to this, and now I don't know, how are you going to solve that quadratic? Well, you could solve it. I'm going to solve it by completing the square here, but you could use the quadratic formula. Right, one way or another, you're going to get the other roots you need. Yay, there we are. Okay, so now we've got -2 as one of our roots. That gives us this term. And now we've got these two non-real roots, a conjugate pair, that give us this piece here. Again, following the same project that we did in chapter 3. Okay, but this already kind of makes you think, what would happen if this was r to the 5th or something like that? I think we'd need a better method than just kind of this kind of factoring. In fact, if you're thinking this may relate to the warm-up, or rather the bonus warm-up, right? Remember when I had us multiply out to the 3rd power a complex number at the beginning? Now that, don't get them too confused. It's not exactly the same example. There, we were trying to find the cube. We were discovering that our cubed, what we got is like 8, not -8. So don't get them confused. This is a little bit different. Very similar, but a little different. It's not exactly the same as the warm-up. So let's actually kind of go through this a little bit and recall the polar form from our warm-up of a complex number. We actually maybe the best way to write it would have been like x plus yi is kind of rectangular form for a complex number in the complex plane. It's got like a location, and then in polar form we can write r times cosine theta plus I sine theta. That's kind of a mouthful, so sometimes you'll hear people say r cis theta, which really just stands for cosine plus I times the sine of that angle. It's a little bit cumbersome to write because this theta and this theta are always going to be the same, right? And we really just want to concentrate on like what's r, what's theta. So this might provide a more compact way. I don't know if your pre-calculus teacher would have done that or not. So just like vectors, right? Again, it's like you've got kind of component form and polar form. They're algebraically equivalent. And if you need to go between them, you know kind of the ways we go about doing that. You just need to kind of use trig, use the Pythagorean theorem to kind of move between those two forms if you have them. So this idea of like finding roots with de Moivre's theorem hopefully is something that you reviewed with the pre-calc PowerPoint. Have I referenced that enough yet? I really want you to do it. If you're getting kind of lost in this, pause the video, stop, and go back and look at that stuff, please. It's going to really, really help you. Okay. So we had said earlier, just in that kind of bonus warm-up, that if we raise something to a power, a complex number, it's a lot of times really like worth it computationally if we write it, even if the problem didn't invite us to do this, to rewrite it in polar form, do our arithmetic, and then come back to rectangular form. Nobody needs to know that you used polar form, right? But it made your calculation way faster, especially if you're going to take something to a high power. And de Moivre's theorem, you heard us talk about during that bonus warm-up, allows you to take the power and like kind of multiply it by the angle. We call it in complex numbers, it's called the argument in here. So what that power did is you come in and multiply it, but it also works with roots. So if you have a 1 over p, so that is you're taking like, instead of to the 5th power, you're taking the 5th root, keep in mind that would be kind of taking a complex number to the 1/5 power. Well, then what that will do is, of course, whatever the R value is for our complex number, of course, that will be taken to the 1/5 power, to, or the 1 over p, if you're looking for the pth roots. But then the argument, the angle will be divided by p. I mean, you're going to multiply by 1 over p, right? And so that kind of gets introduced into the angle. Now, there's something else that's kind of weird here. Mr. Chase, what's going on with this plus 2n pi? That might seem crazy and kind of superfluous, right? But bear in mind that if you were to write the polar form for a complex number, and I kind of made passing reference to this earlier, you would write r cis and then theta. But remember that theta, you have actually a bunch of choices for theta. It could be anything you like that's coterminal to kind of the right angle, right? And so that's what this is saying, is theta could be, we're kind of acknowledging that theta could be theta, but it also could be like any 2 pi multiple added to that, right? And it would still give like a polar representation for our point. And ordinarily that would be kind of, like, why would you even mention that? But here it matters, because as we divide by p, we're going to get divisions of this that are less than 2 pi when we do this division. You'll see in a minute why this makes sense. So you could write this is a fine way to write it, or if you want to write it in this kind of more compact cis notation, you could write it this way. Let's work through an example so you can see what we mean here. Again, if you did the pre-calc stuff, then this is kind of review. All right, so let's go back and do the exact same problem again using this this technique instead. Again, for this problem, you might not like it. You might think it's overkill, but I promise I'm going to sell you on this, okay? Especially from some harder ones. So we're going to start by thinking of writing, we got our number -8, which we want kind of the 3 roots of, the 3 cube roots. We're going to start by writing it in its rectangular form, -8 plus 0i. It sounds kind of crazy to do that. And then we're going to convert that to polar form. So think with me about that. You can kind of use formulas here, or you can also just think, where is -8? Isn't it pointed 8 units kind of to the left on the x-axis in the real axis in the complex plane? It's like in the complex plane, if you're starting at the origin, walk 8 units to the left, and that's where we are. So what polar representation does that have? What do you think? Well, which direction is it? What's like our theta? Isn't that in the pi direction? And how far is it out there? 8 units. So you could use these formulas if you like, but you should also just be able to say that, like, oh, the polar form for this is, in fact, I'm looking here. I guess I didn't write it really here. Let's write it. R cubed is equal to, it's going to be 8. Sorry, I'm writing with my mouse here again. 8 cis pi in this case. There's your polar form, right? It's going to like 8 units in the pi direction. All right, so you could just write that down. You don't need to like use, this is kind of overkill, right? Don't do this, right? Just think about it. Just think about where it is. Some other ones you might want a formula for, but this one, okay. And now we're looking for the 3 cube roots, right? So we're going to let n be 0, 1, and 2 in our formula. And if you let n be 0, you're just going to get, of course, in our argument here, pi over 3. So notice that this pi gets, when we're taking a cube root, we're going to be taking it really kind of to the 1/3 power. And Demovs is going to ask you to do, okay, we're going to end up getting 8 to the 1/3 power. So that makes sense, because we're taking this whole thing to the 1/3 power. And then, of course, the pi, the angle, is going to get multiplied by 1/3. So that'll just be, in that first case, 2 cis pi over 3. But now, see, this is where, if you weren't sure why we were doing this a second ago, keep in mind, this is not actually the only, we wrote this here, but really, we should have said that the polar representation of this is 8 cis pi plus 2 pi n. Again, apologize for my handwriting there with the mouse. Okay, plus 2 pi n, right? Because, like, why did we say it was 8 cis pi? Why didn't we say it was 8 cis 3 pi, right? That's a fine way to write it. And notice that that's in this case, it actually makes a difference. Because if we say this is what that's what this numerator is here, right? It's 3 pi. What do we get when we multiply by 1/3? We don't get the same thing. We don't get the same location for the root in the complex plane. We get 2 cis pi. Ooh, interesting. And now the last example, what would that be? We got pi plus now 4 pi, so that's going to end up being, or, oops, that's a typo. That should say 5 pi over 3. Apologize. So now let's actually work that out. Here, let's see if I can write this. No one will ever notice. That's a 5. Okay. So let's actually write that out. So keep in mind that cis is just our compact way of writing cosine of this thing plus I times the sine of this thing. So what's the cosine of pi over 3? That's right. It's 1/2. What's the sine of what's the cosine of pi over 3? 1/2. What's the sine of pi over 3? Root 3 over 2 times I. Do that again for pi. What's the cosine of pi? What's the sine of pi? There you go. And for the last one, what's the cosine and the sine of 5 pi over 3? That's right. It's 1/2 and negative root 3 over 2. Again, times I. Let's clean those up, each one of those a little more by multiplying in by our 2. And if we've got a 0i, let's forget it. So there we get 1 plus I root 3. There we get negative 2. Hey. By the way, isn't that kind of what we expected when we started? Remember, we kind of knew that before we even began. Like one of the roots of negative 8, one of the cube roots of negative 8 is negative 2. But we also get these other 2 roots using de Moivre's. So again, maybe I haven't sold you on it completely yet because you're thinking, well, I don't know, this seems kind of cumbersome. By the way, once you understand what we're doing here, you probably don't need to write all this out. I've made it look a lot more cumbersome than I have here. Really what we're doing is just being like, keep in mind really what we're doing. The roots of this number in the complex plane, let's look at the geometry here. By the way, there's this final solution again, are here. Negative 2 out like 2 to the left. No surprise there. That's this one. And then we also get 1 plus I root 3, which is right here. And its conjugate down here, 1 minus I root 3. If you have a real number, then its roots are going to come in complex conjugate pairs, right? Like as reflections over the real axis in the complex plane, right? And here's the imaginary axis. So complex conjugate pairs are like reflections of each other over the real axis in the complex plane. And the thing you'll notice is that all of these points lie exactly two units, sorry, my circle's not that great, but all of these lie exactly 2 units away from the origin in the complex plane, right? And they're all separated, they're all equally spaced around this circle. And by equally spaced, I mean they're all 2 pi over 3, right? That's because that's really what we're doing. Sorry, this doesn't look very good. 2 pi over 3 is what I'm writing there. That's really what we're doing here, right? Each time we're adding another copy of 2 pi over 3 each time, right? So that's another way of kind of thinking about this is just think, okay, find one, and then just once you have one, you're just adding 2 pi over 3. Then you're adding 2 pi over 3. Now notice what would happen if we went one more, like, okay, we got one more, and then what if you're like, well, I didn't know how to stop. Like, how do I know that I'm stopping here? Like, what happens if I do it again? If I went to like n equals 3? Well, feel free to do it. If you do it, what will you get? Well, you'll add another 2 pi over 3 here. You'll get a 7 pi over 3 in this argument. And where is 7 pi over 3? Notice that that takes us all the way back to here again, right? And you can knock yourself out and do it, but you're just going to get this answer again, okay? So, feel free to keep going if you want, but you're just going to cycle through these 3 roots now that you have them, okay? Now let's try another one here using a similar technique. The characteristic equation here is, sorry, that's a typo there, r to the 4th equals -1. So we're going to write it in rectangular form. And again, for some reason, I don't have it written here. Really, we have r to the fourth equals, in polar form, what would that be? Again, isn't that just r, and I should have picked maybe a different example here, but isn't that just going to be 1 unit? Like, I'll write 1. You don't need to write 1, but isn't it just 1 unit in the 1 cis pi direction? Don't be thinking that every single problem we do is going to be in the pi direction, by the way. Okay, but this one happens to be. Okay, and then we proceed as before, right? I'll set up 4 of these, and this time we're gonna need 0, 1, 2, 3, and 0, 1, 2, and 3. And this time, if you were to go to 4, then that's when you'll be kind of wrapping around, right? So we plug in those things, and we get, in the first case, just 1 cis pi over 4. When you like, really, it's just, the direction is pi, so we're just like dividing by 4. And then you can kind of think, okay, now let's just do this. I almost want you to stop. Don't look at the formulas. Don't even look at them, right? Just think about this with me. If you were to picture what we just did, right now we're at this point in the complex plane where you 1 unit out in the pi over 4 direction, right? So now we got 4 complex roots. They're all going to be 1 unit away from the origin in the complex plane. And they're going to be equally spaced around a circle of radius 1, the like unit circle in the complex plane. So what's the kind of angle measure between, as we go from one to the next, between these? Isn't it going to be, well, let's see, there are 4 of them. They're equally spaced. It's 360 degrees around the circle. It's going to be like every 90 degrees. So the next one's going to be here. And so now I'm just kind of using my geometric knowledge and visualizing this in the complex plane. This is where our 4 roots are going to be. And so forget all these formulas. They do work out to be the following things. But aren't they just going to be, of course, all of those places? Pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4? Got it. Now, again, we can probably even say what the coordinates of those points are without any work too, because they're unit circle points. They're ones you know and love. Right? This first one is cosine and sine of pi over 4. That's what you got, right? This one over here is going to be, the x coordinate will be negative. Notice these two are complex conjugate pairs. Here, I'll mark them in blue here. This one and this one are these two that we just got here and here. And the last one there in the fourth quadrant there is that one, and I'll mark it in green here. This one and this one are kind of complex conjugate pairs. Again, by complex conjugate pairs, geometrically, we can think about those as reflections of one another over the real axis in the complex plane. Here's the real axis. How am I doing with the mouse, you guys? I think I'm kind of getting used to it. This is definitely not the ideal instructional tool. I didn't realize I'd be writing this PowerPoint. I've been trying to avoid it, but I just couldn't contain myself. Okay, so with my subpar pictures, hopefully this is communicating. So, there's our final solution for this one. It's going to be all of that, right? It's going to be do what you normally do when you have a complex conjugate pair. In green, that's giving the solution here. And in blue, that's giving this set of solutions here. Okay? You've made it. So this is going to require some practice, you guys, and most of it is going to be you practicing your pre-calc skills. Really, as you've gone through this lesson today, you've seen that the differential equations part is really not the hard part. It's really remembering how to do, what are we supposed to do here? We need to be able to do kind of rational root theorem and long or synthetic division and all this kind of factoring skills that you might have forgotten. And then this crazy de Moivre's theorem, complex plane stuff, using de Moivre's theorem to find the roots of a number in the complex plane. So a little trip down memory lane. Maybe you are starting to understand the pre-calc piece better than you ever had before. And maybe that's a good excuse for doing this unit anyway. It's just like an opportunity in the middle of this course to like review your pre-calculus and get back up on your pre-calc skills. It's not a bad idea as a goal to have for us. It's like remember how to do these pre-calc things. So Anyway, I hope you've enjoyed this. Sorry this has been so long. Hopefully you've used the fast forward button. Hopefully you've used like put me on 1.25 speed, or watch this in chunks, something like that. Hopefully this is a lot to digest. So I appreciate you guys hanging with me. Again, as usual, the resources are on this slide, and feel free to check them out. I'll have the slide posted. So have a great one, you guys, and may the joy of math be with you.